Hello everyone. Today I'm here to present Argus++, robust real-time activity detection for unconstrained video streams with overlapping cube proposals. I'm Lijun. This work is a joint effort with my colleague Yijun Qian, Wenhe Liu, and Alexander G. Hauptmann at Language Technologies Institute, Carnegie Mellon University. So in this paper, we are dealing with the activity detection task, particularly in unconstrained videos, where it is untrimmed and with large field of views. There are three aspects in this task: temporal localization, spatial localization, and action classification, where each of them pose unique challenges, and the combination is strictly difficult. So here there is a strict target where we want to detect all atomic activities and perform bipartite matching between the predictions and the ground truths with a straight matrix. But this has been too hard to build a useful system, so there has also been proposed a loosened target, where the system detects either atomic activities such as standing up or continuous repetitive activities such as walking. And the matrix allows matching multiple non-overlapping predictions to each ground truth. We will cover experiments in both these targets in the following sections. So let's begin with the Argus++ framework design. Here is the overall architecture for it. With an input video stream, we perform object detection and tracking with well-known algorithms to perform proposal generation into dense overlapping cube proposals. And with foreground segmentation, we also do proposal filtering to remove stable objects. And then proposals are processed by the activity recognition module to generate confidence scores. Finally, the activity duplication module will produce the final predictions. Here we introduce an important intermediate concept of cube proposals. Proposal refers to a candidate region where activity may occur, and it is the processing element for activity recognition module. In this paper, we use the spatial temporal cube proposals defined as a simple 6-tuple, locating the boundaries in the 3 dimensions. It has a fixed temporal duration when sampled, and it is much simpler than activity instances or tube proposals formats with the moving bounding boxes. So for proposals, we need to sample it in a temporal dimension and refine it in a spatial location. We perform dense overlapping sampling on untrimmed videos to ensure completeness and coverage of any activity instance. Here we can see with the stride less than duration, there is no real boundaries between the proposals, so no activity instances will be cut into half. And for refinement, we select the seed track IDs from the central frame in each temporal window, and enlarge the bounding boxes as the union across the window, so we have a cube with both spatial and temporal localization. Here is an example to illustrate how these cube proposals are generated for this moving sedan in the center. So at a certain stride t, which is almost half a second, we can generate duration 40 proposals, here 0 to 40, 1 to 5t, etc. They are overlapping with each other. And here we can see when they stack together, they cover the duration from 0 to 7t, and this ensures the activity occurs anytime in the temporal dimension. After we generate proposals with detection results, we have only used appearance features, so we further use the foreground segmentation to leverage the motion information. It is a frame-level binary mask for foreground pixels, where we can calculate the proposal foreground score as the average value of pixel masks inside the cube. And then we can learn a filtering threshold by allowing up to some sacrifice true positive. We assign labels to the generated proposals by converting annotation into cube format following the same dense sampling procedure. And we estimate the spatial IOU between the proposal and the ground truth cubes inside the same temporal window. Then we follow the fast RCN in selecting some positive samples and some negative samples, and the remaining will be discarded. As an intermediate step, we want to evaluate the quality of the proposals we generated. This is done by assuming a perfect classifier and using the assigned labels. We pass through these to the following steps and use the official metrics to estimate upper bounds. Different filter thresholds can also be applied, such as spatial alignment, to estimate different upper bounds in different situations. The activity recognition module, thanks to our decent design in the system, is just a multi-label classification task. Here we use the binary cross-entropy loss weighted by proposal scores. We carefully balance the activity-wise positive and negative samples and samples of different activities. When using multiple datasets, we also balance between them. And finally, when we use multiple activity recognition modules, we can do action-wise late fusion to achieve a better score. With the proposals labeled with confidence scores, we need to deduplicate them to produce the final instances. Since we overlapping sampled the proposals, we need to merge them back into non-overlapping ones. This is done by performing an interpolation in the temporal axis. We first merge them into small duration boxes and then expand them back. In the loosened target, this is enough, but if we are working for the strict target, we need to further merge the adjacent instances. Currently, this is done by simply using a threshold subject to a minimum duration. So far, we have covered the system design part, and following will be the experiment results. For implementation details, we are using object detection of mask RCNN with ResNet 101 backbone trained on the COCO dataset. We will apply it at a stride of 8 frames in a 30 frame per second video. The multi-object tracking we use is towards real-time MOT algorithm. We use histogram of Gaussians for foreground segmentation. The proposals are generated with a duration of 64 frames and stride of 16 frames. And we try different classifiers, including R2 plus 1D, X3D, and TRM. We use different evaluation protocols to verify the robustness of our system. Here we evaluate against a series of needs activities in extended videos. It includes the sequestered data leaderboards of MEVA unknown facility, MEVA known facility, which was also hosted at CVPR 2021. There is also an annual self-reported leaderboard using the Vira dataset, needs the track weight series. They both evaluate against the loosened target with PMIS at 10-bit false alarm-based metrics. To verify the Argus++ system in an autonomous driving scenario, we also participate in the ICCV 2021 Road Challenge to perform the road action detection. It is evaluated using strict target with MAP as 3D LU-based metrics. All these experiments results will follow. So first of all, this is the results in CVPR 2021 Activity Night Challenge active and still unknown facility. We can see the Argus++ system poses a 20% advantage over the follow-up team in the NUDC metric. Here, NUDC is a simple integration of the PMIS along the TFA axis. And this is the live leaderboard of NIST active SDL known facility. So far, Argus++ also have a big advantage. Specifically for known facility, we trained on the MEVA and the evaluation data is in the same domain, so we can see the system fits really well. For unknown facility, this is the ongoing version of the CVPR leaderboard afterwards. We are also trained on the same data. Actually, this is the same system with the known facility, but Argus++ still achieves the best results. And here is one of the self-reported leaderboards of NIST Trackway 2021. This uses the Vira dataset, which is smaller, and we can see Argus++ still has an advantage. But in our experiments, we show that the more data we use, the better the system fits. And previously in Trackway 2020, also on the Vira dataset, we have a bigger advantage at that time when we first proposed this series of algorithms. So the previous ones has been extended videos with the loosened target. In ICCV road action detection, we used autonomous driving vehicle videos with moving cameras and evaluated against the strict target of MAP as 3D LU. Here we also achieved the best performance with average MAP of 20. We can see that with a 3D LU of 0.1, the value is 28, but when we make it stricter to MAP 0.5, it's much worse at only around 7% accuracy. so there is still much room for improvement. We perform some ablation study. First, here is the coverage of proposal formats. We estimate the lower bounds of NUDC on the validation side with different proposal formats with different durations and stress. Here, the diagonal lines are the duration equals to stress, for example, 32, 32, 64, 64. And some other values are with overlapping proposals where stress is less than duration. Here we find that the overlapping proposals is generally better than the non-overlapping ones, and specifically the duration 64 and stress 16 has the minimal error when generating proposals. So this is the parameter we have selected. We also evaluate the performance of proposal filtering. Here we can see on the validation side, the positive rate increased from 0.17 to 0.52, and the quality doesn't change much. On the SDL leaderboards, the filtering reduces the processing time from 0.92 to 0.48 real time, while also slightly improve the performance. Here are some conclusion and future works. We propose the robust real-time activity detection system, Argus++, leveraging overlapping spatial temporal cube proposals. It has superior performance in CVPR activity night, needs active SDL, track weight active, and SEC visual challenge. In the future, we are extending strict target into the active settings as well by using biparty matching with spatial localization. And we want to generalize to more scenarios such as UV videos. We are also exploring zero-shot or few-shot activity detection. Acknowledgements. Thank you.